NENOMATICA, where mathematics meets YouTube excellence. Let's display the example. We need to solve the system x squared minus 5x plus 6 is greater than 0, and the fraction 3x minus 21 over x squared plus x plus 4 is less than 0. Step 1. Solve the first inequality, P1. We factor the quadratic. X squared minus 5x plus 6 equals open parenthesis x minus 2 close parenthesis times open parenthesis x minus 3 close parenthesis. The roots are x equals 2 and x equals 3. Since the parabola opens upward, and we want values greater than 0, the solution is outside the roots x less than 2 or x greater than 3. We can record this set as d1 equals negative infinity to 2 union 3 to infinity. Step 2. Solve the second inequality, P2. We analyze the fraction 3x minus 21 over x squared plus x plus 4 less than 0. Check the denominator. The discriminant is 1 minus 4 times 1 times 4, which is negative 15. With a positive leading coefficient and negative discriminant, the denominator is always positive for all real x. Therefore, the sign of the fraction is determined by the numerator, 3x minus 21 less than 0. Solving gives x less than 7. So d2 equals negative infinity to 7. Step 3. Intersect the two sets. We will sketch both d1 and d2 on a number line. Shade d1 from negative infinity to 2 and from 3 to the right without bound with open endpoints at 2 and 3. Shade d2. All real numbers less than 7 with an open endpoint at 7. The intersection keeps only the parts that overlap from negative infinity to 2 and from 3 to 7. So the final solution to the system is d equals negative infinity to 2 union 3 to 7. In this lesson, we will solve a system of rational inequalities using intuitive sign charts and interval reasoning. Here is our example. We will solve the system, find each individual solution set, and then take their intersection for the final answer. Step 1. Solve the first inequality. Notice the quadratic x squared minus 3x plus 8. Its discriminant is negative, so that quadratic is always positive. Therefore, the sign of the whole expression depends on x plus 2 over x minus 3 times x plus 3. We build a sign chart using the critical points at negative 3, negative 2, and 3. We shade where the expression is less than or equal to 0, remembering to exclude where the denominator is 0 and include zeros from the numerator. Step 2. Solve the second inequality. We factor the numerator and denominator. Use difference of squares and standard factoring. Then we construct a sign chart for the critical points at negative 4, negative 1, 1, and 2. We shade where the value is greater than or equal to 0. Zeros at the numerator are included. Undefined denominator points are excluded. Step 3. Intersect the two solution sets. Remember, the solution to the system is the overlap of the individual solutions. We overlay both results on one number line and highlight the common parts. The final answer is the union of the overlapping intervals. In this example, we will solve an absolute value inequality for the parameter a, and we will do it in 4 clear steps using discriminants and interval intersection. Step 1. Use the absolute value rule. If the absolute value of u is less than k, then negative k is less than u, which is less than k. Apply that to our expression. This becomes negative 3 is less than the rational expression, which is less than 3. Step 2. Check the denominator. We will show that x squared plus x plus 1 is always positive, so multiplying the inequality by it preserves the directions. For a quadratic, ax squared plus bx plus c with a positive and discriminant less than 0, the quadratic is always positive. Here, a is 1 and the discriminant is 1 minus 4, which is negative 3, so the denominator is positive for all real x. Therefore, we can safely multiply through to get a pair of inequalities without the denominator. Step 3. Split the double inequality into 2 separate ones and simplify each. First, x squared plus ax plus 1 is less than 3 times x squared plus x plus 1. Move everything to the right. 2x squared plus quantity 3 minus a times x plus 2 is greater than 0. Second, negative 3 times x squared plus x plus 1 is less than x squared plus ax plus 1. Move everything to the right. 4x squared plus quantity a plus 3 times x plus 4 is greater than 0. For both to hold for all real x with positive leading coefficients, we require their discriminants to be negative. Play button step 1. Since the leading coefficient is positive, a quadratic is strictly positive for all x if and only if its discriminant is less than 0. Let's display that rule. Now apply it to 2x squared plus 3 minus a times x plus 2. The discriminant is open parenthesis 3 minus a close parenthesis squared minus 16, which must be less than 0. That simplifies to the absolute value of 3 minus a less than 4, which is equivalent to negative 4 less than 3 minus a less than 4. Solving for a gives the interval negative 1 less than a less than 7. Play button step 2. We repeat the same logic for the second quadratic. We'll reuse the discriminant rule. The discriminant is open parenthesis a plus 3 close parenthesis squared minus 64 less than 0. This becomes the absolute value of a plus 3 less than 8, or negative 8, less than a plus 3 less than 8. Solving for a yields negative 11, less than a less than 5. Play button step 3. Take the intersection of the two intervals. We have negative 1 less than a less than 7 and negative 11 less than a less than 5. The intersection is negative 1 less than a less than 5. That is our final answer. Example. We will solve a system of 3 quadratic inequalities step by step. The system is x squared minus 5x plus 8 is less than or equal to 0, x squared minus 3x plus 6 is less than 0, and x squared is less than 1. Step 1. Analyze the first inequality. We will use the discriminant property. Delta equals b squared minus 4ac. Here a equals 1, b equals negative 5, and c equals 8. So delta is 25 minus 32, which equals negative 7, less than 0. Since delta is negative and is positive, the quadratic is always positive, so it cannot be less than or equal to 0. Therefore, D1 is the empty set. Step 2. Analyze the second inequality. We again use the discriminant test. A equals 1, b equals negative 3, c equals 6. Delta equals 9 minus 24, which is negative 15, less than 0. With delta negative and a positive, the quadratic is always positive, so it cannot be less than 0. Therefore, D2 is the empty set. Step 3. Analyze the third inequality. Use the absolute value rule. If x squared is less than a squared, then absolute x is less than a. For x squared less than 1, we get absolute x less than 1, which means negative 1 is less than x, which is less than 1. So D3 is the open interval from negative 1 to 1. Let us visualize this interval on a number line. Step 4. Take the intersection. The intersection with an empty set is empty. Therefore, the overall solution is D equals D1 intersect D2 intersect D3, which equals the empty set. Recap. We computed the discriminant for each quadratic. The first two had negative delta and positive a, so they were always positive and did not satisfy the required inequalities. The third gave the open interval from negative 1 to 1, intersecting with empty sets yielded an empty overall solution. Example. Solve this system of inequalities. 5x squared minus 7x greater than 0, and x squared minus 11x plus 30 less than 0. Step 1. Solve the first inequality. We'll factor the left side to find its critical points. Use factoring of a quadratic with a common x. 5x squared minus 7x equals x times open parenthesis 5x minus 7 close parenthesis. The zeros are x equals 0 and x equals 7 over 5. Now build a sign diagram for the product. Positive to the left of 0, negative between 0 and 7/5, and positive to the right of 7/5. Since we need strictly greater than 0, the solution set is negative infinity to 0 union 7/5 to infinity. Step 2. Solve the second inequality. Use factoring of a trinomial into two linear factors. X squared minus 11x plus 30 equals open parenthesis x minus 5 close parenthesis times open parenthesis x minus 6 close parenthesis. The zeros are x equals 5 and x equals 6. For a monic quadratic, the product is negative between the roots and positive outside. Since we need strictly less than 0, the solution is the open interval 5 to 6. Step 3. Intersect the two solution sets. The solution to a system is the intersection of individual solutions. Intersect D1 with D2. The intersection is the open interval 5 to 6. In this lesson, we will solve a system of cubic inequalities using factoring and sign charts. We'll start by clearly stating the example, then solve each inequality, and finally take the intersection of the solution sets. Step 1. Solve the first inequality. We'll factor the cubic expression by taking out the common factor and factoring the quadratic. Start from x cubed minus 11x squared plus 10x greater than 0. Factor out x. Then factor the quadratic to x minus 1 times x minus 10. That gives roots at 0, 1, and 10. Now we build a sign chart across the critical points 0, 1, and 10. From the sign chart, we read the solution. Open interval from 0 to 1, union open interval from 10 to infinity. Step 2. Solve the second inequality. We'll use the same factoring approach. Start from x cubed minus 12x squared plus 32x greater than 0. Factor out x. Then factor the quadratic to x minus 4 times x minus 8. The critical points are 0, 4, and 8. Build the sign chart and identify where the product is positive. We find the solution set for this inequality is open interval from 0 to 4, union open interval from 8 to infinity. Step 3. Take the intersection. We combine the two solution sets and keep only the x values that satisfy both inequalities. The intersection is the open interval from 0 to 1 union the open interval from 10 to infinity. In this example, we will find all real values of m so that the point A of m squared minus 1 comma negative 2 m squared plus 7 m minus 3 lies in the second quadrant. First, show the example label. Now display the problem statement in bold orange. Step 1. Points in the second quadrant have x less than 0 and y greater than 0. Show the rule in a tip box. Now write the system of inequalities for x and y. Add a quick challenge prompt for the next step. Step 2. We solve m squared minus 1 less than 0. Move the 1 to the right to get m squared less than 1. This means the absolute value of m is less than 1, so negative 1 is less than m, which is less than 1. Illustrate this on a number line. Step 3. Solve negative 2m squared plus 7m minus 3 greater than 0. First find the roots by setting it equal to 0. Compute the discriminant, b squared minus 4ac. Use the quadratic formula to find the two roots. Because the leading coefficient is negative, the parabola opens downward, so it is above the axis between the two roots. That gives our interval. Step 4. Take the intersection of the two solution sets. Intersect negative 1 to 1 with 1/2 to 3. Visualize the overlap on a single number line. State the final answer. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.